Welcome everyone to another in-depth low-level live stream here, only with instructions on architectures and assembly view live here on this channel. Today what I actually do between the YouTube videos when I try to actually get work done. Here with this ARM Mac, previous videos, this M1 and similar stuff. And so it turns out from our commercial software, which probably was working on ARM because certainly it's very portable source code and stuff. But some scanners were not, depending on what source code was used, because hundreds of thousands of lines of code in the meantime and stuff, and drop frames. And we finally debugged that and nailed that down. No, not right now, we're in the middle of a live stream. So it turns out, except drop frames. That was, let's see, so this is, here should be, so this is the Apple Darwin kernel GNU stuff, ARM, and so it turns out this was some probably undefined behavior of C, because certainly C, amazing assembler, preprocessor, front-end, recurring theme here, amazing stuff. We got this, not. And for that matter also C++, obviously. And so it turns out the difference is that, so I distilled this down to this test sample. Obviously this is not our real world code, certainly our award-winning and one of the best document scanning applications is made out of more than main double printf return. So this is the reduced test case for the code that was working. So what was the issue? So a lot of code was running with millions instructions a minute, and like some scanners were scanning and some scanners were not scanning. Bizarre stuff was happening, and it's like, what the heck is even going on here? So after I had to do some guru meditation here, I would want to do more amazing stuff, but yeah. ARM Apple M1 Guru meditation, here it is. So it turns out we had some code that was using obviously mixing integers and floating point stuff, like you would probably do. Questions, thanks for joining and asking questions, answers later, end of this motor stuff. And usually whatever you do with physics and math and stuff and device drivers, eventually you save it to a file, send it to some USB device and stuff, and usually at the end of the day you probably often need some integer, or for example image processing, like in GIMP, Photoshop, Pixelmator and all those fun stuff. You would probably do some image processing potentially in floating point, depending on what you're doing, and at the end rounding this to 8 16-bit color values. Anyway, so this is totally normal code, and what we were doing for this compression, but it doesn't really matter too much. But long story short, the issue is casting a double. So also, if you're new to this channel, we usually do here relatively in-depth computer science stuff. And I will also, if everything here, if you understand nothing here, then probably you want to share, like, and subscribe, because I was already teasing and thinking about do some programming 101 that is a little bit more lightweight than undefined behavior in C and C++. So what actually I probably should read the standard whether this is really undefined anyway. So on this code was working for 11 years, I think. So this code was committed 11 years ago, because our company exists longer than yesteryear. And so for 11 years it was working on Linux, on Windows, on x86, on AMD 64, on ARM, probably even on ARM 64, Spark, MIPS, and everywhere in between. Basically a PowerPC, it was basically working everywhere, right? Until today, Apple's M1 and latest Uint Clang compiler. So what is happening? So this is just some really stupid code. I only want that the compiler doesn't optimize this entirely away. This is why I could probably also do some extern double stuff, but I wanted to keep it super more simple. So I intentionally create here a negative double floating point value. Probably it works the same with single precision floating point. All the details do not really matter. What only matters is that we get some user input value here, that the compiler doesn't optimize it fully away anyway. So, and I create this negative. I could, of course, do a command line parsing, but it's a distilled reduced test case. This is why I keep it most stupid simple. So we create your negative value like -1 depending on how many arguments you supply to this test thing. If you run it with 1, 2, 3, 4, 5, then you have there -5. Because this only happened with negative numbers, right? And this, what I do here is I cast this here to an integer, and so actually, so this is working. So what this is doing is printing like long double, just in case 64-bit, the magics of amazingness of C format printing, and just to print this out, right? This is everything we need for this distilled test case. And when we run this, let's just run this. So okay, this outputs. Oh wait a second, -1. What have, right, this is, oops, also this is what we wanted. So -1, this is what we want. But I was using here this is signed integer. If we make this an unsigned integer, so actually our code was working with unsigned integers, just so this is what should be the output, like it should be -2 or -1. However, we wanted an unsigned integer, and what you would expect is that the way this computer numbers work in two-complement representation with fixed point integers, probably upcoming low-level programming series, don't forget to share, like, and subscribe, if this doesn't mean something for you. Anyway, so we have bits, we have like 32-bit of all your 32 or 64-bit computing, and those bits, two complement at a time, can represent negative numbers, working the way from 0 -1 is then all bits set, because 0 plus 1 is obviously 1 and plus 1 is 2, and minus, so if we subtract 0 -1 from 0 in this two complement form, we get all bits set. We get like 1 1 1, like 32 bits, 1 or 64 bits 1. So, and this code was expecting to get a two complements form of an integer, like basically truncated to the nearest integer, what you could also do with other library functions of rounding to nearest integer. Anyway, so uint, let's gcc test, or wait a second, I probably used clang test c and a.out, and this returns 0. What the heck? Why does it return 0, right? So two complements form. So we have -1. This should be all bits set, right? But it returns 0. This took me hours to find, because obviously our program was behaving relatively, given this was some virtual machine code and stuff. So basically what happened is, after some hours of guru meditation, debugging through our virtual machine stuff and some related debugging code, and I was actually debugging. I was debugging everywhere, right? USB stuff, because it didn't make sense. All the values I saw, like this USB data didn't make sense. Other stuff didn't make sense, until I realized, wait a second, what is happening with these negative numbers here? So basically, in this, all the negative numbers became 0. And if we compare this to my epic AMD thread-ripping Ryzen here, from which we live stream here from our Linux, same program. The only thing I changed, but that doesn't really matter too much, I changed this. We can change this to unsigned, and so the same program, right? I just scp'd that here over gcc and a.out. And this returns here a relatively large number, which is all bits set in a 64-bit integer. This is exactly what, in my opinion, this should be. Probably very light. Truth be told, I'm not even blaming Apple too much here, because probably that is, don't manually truncate a floating point value, maybe. Because C, actually, I probably make a dedicated video sometime soon, like a list of 20 or 50, because the C standard is full, this kind of undefined behavior, of casting this, of calling that, of whatever. So many, really many undefined behavior stuff. To illustrate this better, if we use D for decimal instead of unsigned, we actually get -1. However, because this is the way two complements work, right? So this only works by accident, because the processor doesn't even know that we casted this here to an unsigned. So we have all bits, we have -1 in 2 complement integers. This is all bits set. And although we cast this to some unsigned for testing purposes here only, we get an integer. In my opinion, this is how that, although probably implementation, implementation defined and undefined behavior. But in my opinion, probably C would also be less buggy and more stable if there would be less implementation defined and undefined behavior. So even this only works by chance, and I don't even want to say that this should work. This unsigned integer to this like only works accidentally due to the way 2 complement binary numbers work in computers, because we see what happens here when we use X for hexadecimal. Then we see here obviously that is much more readable than whatever 18 something quadrillion whatever something that might be. So yeah, this is why. If you ever wondered why so many debug code print stuff in hex, then it's like, yeah, this kind of stuff is nicely seeable. So yeah, x86 behaves probably how this should be. And when I did this extra effort just for this YouTube video, wanted to share this. So again, this is not a bug in Apple's M1. At least I guess so. We look into the ARM either in a second. So I don't want to say Apple is doing something entirely wrong. It's just probably, I would not necessarily promote this kind of behavior. This is also my recurrent critique of C and C++ of, yeah, too much assembler, glorified assembler preprocessor. If we take a look, so my Mac here, my fancy ARM Mac, if we diff this, so the only difference of this two, and this is the same of this distilled test case, the only difference is this floating point conversion. So this is previous video. I have already instruction set architectures of ARM, MIPS, Spark, RISC-V, rendition verity, x86 and other such stuff. So this is floating point conversion with signed and unsigned towards 0. So this is actually floating point conversion towards round towards 0, signed and unsigned. So this makes sense. So the difference between just casting this in C is just this one different instruction selected by the compiler. And this is this instruction, right? fcvt set u, scalar fixed point, floating point convert to unsigned fixed point, rounding towards 0. Scalar, this instruction converts the floating point value in the single instruction multiple data and floating point source register set to 32-bit or 64-bit fixed point unsigned integer using round towards 0. And so this is a little bit fishy here. So I'm not sure if I have another ARM processor, because I have a lot of stuff here, as you've seen, SG Octane and P3 and also the PinePhone somewhere here, previous video. But I'm not sure if the PinePhone with A64 has this instruction, because this is a relatively new instruction. I think at least they say here, maybe I try this later on the PinePhone, just on a previous video, because they say here ARM version 8.2, and I'm not sure if the PinePhone has 8.2 or only 8. Anyway, so the problem is, I read this here before the video. I'm certainly making a little bit of preparation before the video. I'm not sure, is this focused? No, not that it matters too much if it's focused. But they don't really see here how this works, because in my opinion, I've never seen this in any other processor so far. So this kind of undefined behavior, although I have like nearly every other CPU instruction set architecture here from ARM, otherwise ARM. Actually, my first non-PC was ARM, the Psion Revo, previous video, in 1998 or so. MIPS, Spark, PowerPC. I probably can do more testing. Maybe actually I built here even better infrastructure. You've seen here in previous videos, I have a lot of stuff already installed and standing and stuff. But of course, it takes quite some hours to turn everything on. Maybe I actually create my own testing facility that I can run here like wake and SSH to have here a stack of stuff on standby, so that I could like automatically dispatch this to all hardware stuff to test this more efficiently. Because so this, as far as I've seen, this doesn't mention this ISA document here, how this should be behaving with negative numbers. This is a little bit funny in my opinion that they don't really clearly mention this. However, they have here a library function equivalent here. So as you see, how this should behave, they have here integer d, integer n, and then type of, then depending on what bits are set, whether this is previous video, 64-bit or 32-bit, float, and so on, and even maybe being undefined. But how this should work in, so if scalar 5 undefined otherwise, integer fractional bit 64 minus u in scale, 64-bit, is this the final result? ND fractional bit, yeah, because if you click on this uint, then here is a library pseudocode shared function common, also doesn't really jump to the, here, common uint, here it is. And I can also make this larger for you. And so uint, so this is apparently the equivalent. So as I said, this instruction doesn't, instruction manual doesn't really, as far as I've seen, specify this. Only here as an example of pseudocode in this library. So this would be integer uint for bits n in their pseudocode notation here. So result is 0. So if we go through this pseudocode, so similar to on my previous FPGA Verilog videos, how you would program this. So they write here for I from 0 to n bits. So this is bits n, so 32 or 64 bits, minus 1, obviously, because computer science, everything from 0 to n minus 1. So if x, so if at the input x, bit I is set, then the result, so they are basically creating here a result that equals all the bits. This is of course highly inefficient pseudocode. You would probably not implement this in hardware like this. But basically, I'm not sure if this implementation at Apple, this is why it's always good to have a second processor, right? Because, as I said, for me, as you see here on the AMD Ryzen, for me minus one means all bits set, right? And if you have the only question is, the floating point representation is not exactly like this. So this is even still this, in my opinion, with this pseudocode, this still leaves a little bit to be desired of in interpretation, because it's not entirely clear how they mean this to be treated in terms of floating point input for this uint thing here, because the floating point representation with exponent and lattice and signed bits is of course not exactly this also. And this is maybe they take the floating point like without the signed bits. I mean, this is really a little bit fishy in my opinion. This is also why stuff in C is often a little bit fishy and implementation defined and undefined, because near whatever the processor is doing in that case. And you see that obviously differs here in terms of Ryzen, all bits set to ARM, just returning 0. Theoretically, let's see if we can create the if we output on the Apple ARM the full yeah, because it doesn't work as simply as that. Let's make a union. I actually did not try that before. Union double union means we overlay both things there inside one thing. Double D and uint 64 I, and we make this x, and then we say here x dot d should be that, and we print then out x dot I, just to print you the bit pattern of the floating point representation. Of course that doesn't work because I have here some really stupid typo. So yeah, this is the representation, as it probably looks somewhat correct, I guess. And the only so this is a little bit near if in which way does it even make much sense of, I think it could be correct. Not entirely, whatever. But so what happens here is that the floating point representation is, of course, floating point, as the name said. And so this is a sign bit, and that should have a nice diagram of sign bit. And here's the exponent, here's a fraction, by the way, fraction sounds. Anyway, so exponent and fraction, and this is why this ARM documentation leaves a little bit to be desired. And I'm also not, theoretically we could make, because this looks a little bit strange in terms of endiness, we can just test, oops, I wanted actually test 2. Let's copy this here as well, and test 2, compile that. And yeah, this is actually on the horizon, obviously the same representation. On big endian it would be byte swapped, obviously, but the modern ARM stuff usually is little endian, although big endian previously existed in the ARM world too. And yeah, so 1, 2, so C008, C008, that probably C0, yeah, so the bit representation is as expected, IEEE floating point stuff exactly the same, and again sign bit. And when we don't make this negative here, then of course the sign bit flips, and previously this was that bit set, and now it's not set for negative numbers, as most likely seen here somewhere with significant digits of sign, whatever. But yeah, this is a difference in floating point versus 2 complement integer fixed point representation. Here a negative and positive number is exactly the same with all those bits except the sign bit set, and this is why, in my opinion, this ARM documentation here leaves a little bit to be desired to actually understand just from the documentation how this should behave. But yeah, not so, in my opinion, the ARM standard, maybe there are better standards. Actually, did I click on, actually I think I clicked on that and that didn't write this message, because wherever that is. Anyway, so yeah, that is that, and this it's somewhat annoying and surprising that in 2020 we still have such implementation defined behavior and of decades working code decades of code breaking yet on new silicon. I'm saying it's undefined because a lot of this stuff in C are usually, if you are doing a little bit non-standard stuff, which you easily and often do in C, then you quickly in the C standard run an implementation or undefined behavior. And even from reading the standard, so even if I do my homework here and read this, then also this is the wrong thing, then even, where would that be? Overview, don't really want to overview. Again, even from this documentation, it doesn't mention here what should happen with negative. So the word negative it's so not even ARM is specifying what should happen with negative numbers, except this one uint cast pseudocode stuff. Let's see, integer d, what do they have here? Can we make here a little bit better? xd dn f bits of integer d uint rdn. What is rdn? It's a little bit. But anyway, even this, I repeat myself just answering the questions, but even this documentation for me are not entirely clear. Usually I would prefer that ARM is specifying for negative values that and that should happen. I would hope that ARM has internal test cases. Obviously they should have some simulation stuff, and probably Apple tested against some official ARM test you. That's probably this kind of stuff that you also pay some millions for licensing that IP. But here, assembly symbols, something, f-bits, double precision, something. So operation again. So here's the operation. Wait a second. Here we have. Actually, here's some better flow that I previously. Maybe I didn't scroll enough down. Here's some better operation. So here's some better operation of check FP and SIMD enable 64. Otherwise, if that's not enabled, it throws an exception, or not throws, generates an exception, or traps with an exception. Floating point value fn, so this is probably floating point values like indexing into that register array, getting that, and then floating point value z functional bits true, FCP round towards 0, int value of true, so that would be probably some nice library function. That's probably a better library function of what should happen. Convert n-bit precision floating point up to m-bit fixed point with f-bits, fractional bits controlled by unsigned. And actually, so here's unsigned. Here's okay, this is Boolean unsigned. So actually, probably with this, we can determine what ARM was thinking here. So where do we have this? We have assert n in z, m in z, fractional f-bits greater equal 0. Rounding, not rounding odd, unpack, fp unpack, type signed value. Let's see, type signaling num or quite. So this is not a number, so this is floating point if the type is a floating point type. Signaling none or quite none, whether signaling versus quite is whether it should throw or not throw. I always say throw. Whether the CPU should assert and generate an exception or process this quietly. Then scale, so value by fractional bits, result round down, so integer result. So this should still be like a signed integer. So this should be, in our -1 example, I would expect this to be all bits set, f, and so on, error, value minus real stuff. So determines this is rounding mode, so round something, we round towards 0, so round up, error, integer result stuff. Generate saturation result and exceptions, so result overflow, saturate, probably this is quite, I guess, set quite probably int results. So this is, so if overflow, actually, you know what, I still didn't see the use of unsigned in here. Controlled by unsigned. Here's int operand op, so we probably need to look there already. Int if unsigned, then, but okay, we are, however, although I found here this better pseudocode, we are back to the same uint function. So integer bits n here of x boolean unsigned is result unsigned, then uint else. So this is using the same uint. So basically this uint we had previously, so what we said in the beginning of the live stream still stands. Also this jumps slightly, or maybe this is a zooming because I have 100, so probably the hyper links probably scroll here wrongly due to 133% zoom. Anyway, probably. But so we are back to this, what we have had previously of iterating, of like theoretically iterating and pseudocode over all bits and accumulating the 2 to the power of bit and ending this up. So I'm still, so this is really unfortunate that even reading so much pseudocode at the end of that, we are still not sure, at least I'm not sure. Leave me in the comments below your show. Did I have the PinePhone already? I have here this hardware listings, not only for you to check if someone tried the stuff, but also for me. I recurrently use our own hardware listing here to check, for example, stuff. Would this have be architecture 8, variant 0, revision 4? Okay, but from this, not entirely sure if the PinePhone, probably I would need to power it up and see if, yeah, not sure if that is 8 point. Actually, we probably, this is all winner. I only mentioned this to check whether this other second party CPU behaves the same. ARM version 8. Yeah, so they don't mention .2 here, so even with that, wouldn't necessarily be sure if it supports that instruction, if this is a strict 8.2. Anyway, so yeah, isn't that fun at the end of the day? So how did I fix this? Of course, I just casted this but yeah, this is this kind of stuff of just casting this here differently to satisfy the compiler and CPU. But yeah, this lesson learned, even with very simple floating point integer assignments, whether truncating, rounding and stuff, you can in 2020 still, even with 20 years experience, it worked everywhere until ARM version 8.2, and yeah, a little bit questionable pseudocode documentation, of which it's still not entirely clear if that is. Yeah, actually, maybe I should. Wouldn't it be nice if we discovered that this processor is violating the ARM version 8.2 standard yeah. If you worked on such processes and have this to test, let me know what you think. Maybe I should actually give them the. Yeah, I mean, obviously Apple wouldn't recall this stuff even. Probably it's undefined in implementation. Probably it's fine. But wouldn't it be cool if that would be a real bug here live on this channel? But anyway, long story short, write as much verbose, readable, standard conforming, certainly not relying on undefined and implementation defined behavior. Implementation defined meaning like doing crazy math stuff that only works on one CPU because special truncation mode, which actually 386 did back in the day, because 386 had 80-bit precision instead of 64-bit, as ironic as it is for back in 1986 or whenever that was, or was it already the 8087? Anyway, of course nowadays we don't have this, we usually don't use this stupid and crazy 80-bit precision mode, because if you relied on your floating point stuff to have 80-bit precision, and it would not be numerically stable with 64-bit on PowerPC and Spark and MIPS and stuff, then obviously you run already in problems 20 years ago. But yeah, 2020, isn't it fun wasting hours with new Apple Silicon just because amazing new, a little bit underspecified and ARM functions and stuff. Anyway, that's it for this video. We will have fun implementing more just-in-time compiler stuff and here on this channel. I hope you learned something. Leave me in the comments below what Peter writes. There is no documentation for the processor. Well, it is ARM, and it's an ARM processor, right? So I mean, the general ARM stuff should apply. That is at least the instructions of architecture previous video. So I mean, at least you should be able to rely on that. And in any case, it's super annoying when in 2020 you have 20 years, 30, 40 years of code that just work everywhere, and then the latest and greatest ARM stuff breaks it silently. It's like, yeah. Peter says, since it's not standard, a non-standard processor, that's not entirely true. It's an ARM64 processor, so it's you can't just say it's a non-standard processor. It's a totally standard. It's their implementation of how to do this, but if it's running ARM code here, obviously it should execute the ARM code as defined in the ARM standard. Otherwise, yeah. So Peter Suvara remembers writing floating point to fixed point functions assembly stuff. Yeah, so I mean, normally, as you see this in modern processors, it's not so much to write. By the way, for the fun of it, we can look at this object dump of diff again. Assembly, this is just nowadays just floating point convert x10 to d stack pointer store d0 stack pointer. Yeah, so this is x10 to d0 floating pointer x0 x10. Whatever. So yeah, it's not much to do on assembly level than just one instruction to do this stuff. We could theoretically take a look how this looks. So this was GCC on x86, object dump, disassembly, a.out, like old, doesn't matter too much, and then int. And actually this is way more different than just an ARM. Yeah, on ARM it was just one instruction. Here it is whatever. Maybe it becomes clearer with O2. Optimizing a lot of surrounding noise away. Probably this tilts it better. Wait a second, what? Ah, this is probably both the same. Let's see. What this is. Oh wait, on x86 this is the same. Wait a second, interesting. So this is although, is this? Yeah, actually this is an interesting point. Oops. Because as I said, I would also, unless we made here some -1 diff object dump. But this is also exactly what I would expect with that retains the same bit pattern. And yes, so with this is a little bit interesting that without optimization it's so different. Probably some stuff changed a little bit, and then it takes the optimizer to optimize all of this stuff away. But yeah, so on x86 assembly output of this two cast entirely the same as this is also what we wanted, right? We wanted the truncated integer bit pattern. Anyway, yeah, interesting finding here. I hope you learned something. What else do we have here? Peter shared the video on Twitter. Thank you for that. Peter actually searches for some of the assembly compiler for the one. Is this the first time I have seen anything? It's just standard ARM64, right? So even Apple says it is ARM64 here. If it is not, yeah, this is on screen. So I mean, Apple is not. Apple always says Apple Silicon, but in reality, it's just one standard, hopefully mostly standard conforming implementation of the ARM instructions and architecture. So nothing really secret there. Dash asks, is it better for the documentation for the MIPS implementation? Good question. I don't know. I mean, the problem is usually when I look at this documentation, it makes quite a kind of sense. Usually, I would not even have criticized this. Only if you sit here with some undefined behavior, like previously 386, 486, or Pentium, fdiff, FOOF, and whatnot bugs. Then only when strange stuff and undefined and erratic stuff happens, and you take a look at this, and only then it actually pays off to have really precise documentation, because before you have some really strange behavior, you don't actually usually probably never look into this library pseudocode. Otherwise you only, I mean, this is also a little bit the danger, right? And why bugs and like really critical and devastating bugs happen, because like myself, I would only look here at the high level of rounding, and I would not even come to my mind to that this could return 0 for any negative number here for this unsigned case. So because it doesn't even specify this, right? So this is why this is really peculiar. So yeah, we asked at the question at the very beginning. Sorry to answer this, I should have answered this a little bit earlier. Say Manish asks, would you recommend Apple M1 for developers? Well, it depends. If you need this for a commercial Mac application today, then probably yes. If you don't need this to ship a native Apple ARM64 application today or the next weeks, then probably it is better to wait a little bit, because right now this is only the first and lowest performance implementation, and there is certainly, like as usual, if you don't need it today, next month or year, it will for sure be like M1 or whatever they M1X or whatever they call the higher core count for the 16-inch MacBook Pro or iMac or Mac Pro or whatever. So if that fits what you want, then yeah, I would actually not buy it. Usually if we wouldn't have here this award-winning and one of the best document scanning applications, because I'm not very satisfied with Apple hardware, with vendor logins, with security, with locked down stuff, with soldered memory, soldered SSD, previous videos. So yeah, unless you really need this, otherwise, if you don't need a Mac, or there are certainly other ARM things that are not necessarily that performance. If you need that performance there, or if you need better performance, then certainly there's some epic AMD thread-ripping stuff out there. Anyway, I learned some interesting things as usual. I hope you learned something too. Although what I really don't like is that this kind of stuff, I mean, it doesn't even generate a warning, right? For me, it is a little bit annoying that this kind of stuff wastes so much time. This is also why does POS1 not work? Maybe Alacrity, whatever. I wonder if it generates a warning with vextra format specifier, but argument, okay, but it still doesn't. So it's a little bit, I mean, so much to warnings and better compilers, because it didn't even generate a warning for this stuff. So it's not like, hey, you are truncating your floating point stuff, and it, yeah. I also wonder if this instruction, I mean, do you really ever want something that truncates half of your, I mean, this is a really interesting instruction of just truncating this to 0, or rarely have I seen that, but leave me in the comments below. Sam wrote, same ISA as Raspberry Pi 4. Yeah, sort of. I'm not sure if Raspberry Pi 4 has ARM 8.2. Maybe it has, maybe it hasn't. 8. ARM 64. Maybe we should click on Pi memory, Pi, where is even Pi 4? Here's some, what graphics? Here's Broadcom something. Why did they not? That is a little bit. What is it? No other mentioning? Yeah. So much to Wikipedia. Raspberry Pi. Yeah. Forum of Broadcom. Here's Broadcom. So Cortex. So they also. I saw they already V8. If they only write here V8, then I would not count. So maybe it's a little bit newer instruction set architecture in terms of having a couple of 8.1 and 8.2 instructions potentially. Actually, we could check of touch test. Oh, actually, we could just Clang DME tests C and let's. Yeah, of course, some Unicode liberation usually seen here. Either V8 or ARM8. Yeah. Actually, I wanted to check what kind of things it sets here. Because the compiler showed iPhone ARM. Yeah. Brave New World. Is the ARM 64? Actually, it has here even 8.3 even. This is what I saw. Arch 8, I wonder, does it not have Arch 8? Does it not have... interesting that it doesn't set 2 though. I would expect this to also set 2 and 1 then. But yeah, that's what Clang defines there. Anyway, that's it for that. But yeah, this is why stuff takes a while. Software costs money, and this is what makes because people always think just click some buttons together and ship it. But yeah, at the end of the day, it takes a little bit more, especially if you have non-trivial software that does a little bit more than having 5 buttons. Interesting, they don't specify this here further. They have here only, well, it's Wikipedia, right? So, but they have here only V8A. That was 2011. 8.2. Here's 8.2, evolution and delivery. So we have, actually here are some Cortex something. So yeah, they are actually, here's Apple Vortex. Yeah, so this is here officially listed as Apple Vortex Tempest 12X. And actually this is even ARM version 8.6. So I mean, it's not entirely, because this Broadcom is somewhere. Not even listed here. I mean, this Broadcom stuff is really not the state of the art. Not even listed here. So, but yeah, this here, we have here mostly Apple stuff of 8.3, 8.4. So yeah, probably I will not have other silicon to actually test or Cortex A. Actually, we could. 8.2 is actually already Apple Monsoon and Mistral A11. So yeah, I mean, this Apple stuff, not only previous video, pretty snappy and relatively high performance, especially for the power consumption, but also relatively state of the art. There's only few stuff. I mean, here's Marvel Thunder X3 for A3 Plus, but otherwise, I wonder which other silicon has Apple, has ARM V8.4, 5 and 6. Probably only, if at all, then some Google, Amazon, whatnot. But anyway, yeah, that's it for this video. Lesson learned: don't rely on undefined behavior. But this is also the problem with C, right? You write code, and you think it's sane. You just like truncate some floating point to integer, and it blows up 11 years later. So much to, yeah, how should you actually have known? The compiler doesn't even tell you, like, hey, you make this implementation defined and undefined, and better don't do this. Like, no, it compiled fine everywhere from Microsoft Visual C to GCC and Clang, and even today compiles fine just on Apple's silicon. It truncates all negative integer or all negative floating point range to 0. Whether or not that is in accordance to the specification, leave me in the comments below. That's after repeating this 5 times everything for this video. I hope you learned something. Peter Suvar writes, so how do you write assembly code and take advantage of the neural engine GPU and performance course? Never seen ARM docs for the GPU. So this is not ARM, right? So Apple's GPU previously, on previous iPhones, they had PowerVR. Previous video, we have here some fine Kuro and Intel GMA 500 that we want to reverse engineer if it's a snowy, rainy winter day, sometime soon between now and forever. Probably forever, a couple of years or something. Anyway, so one day probably we have PowerVR reverse engineering. You probably want to share, like, and subscribe. We have already reverse engineered Matrox, Parhelia, and other 500 scanner drivers, so it's not like I don't usually do this. So this GPU stuff is PowerVR, or nowadays Apple's copy and clone. They allegedly pay PowerVR because I think PowerVR wanted to use them or something. So they agreed there on some licensing, IP licensing stuff. Because Apple allegedly copied there, inspired there quite a bit of Steve Jobs' famous artist steal there, of good artists copy, great artists steal. So yeah, obviously they stolen everything from PowerVR. So it's said to be quite close to PowerVR. So you program this with Metal, or aka otherwise close to Vulkan and stuff. So you program the GPU like you program NVIDIA or AMD GPU, usually with high level OpenGL, OpenCL, Vulkan, Metal, and other fun stuff. And the neural engine, you would use their frameworks, right? So for the neural engine, they document nothing, and this is a driver, right? It's a additional. It's not in the main CPU space of ARM. Most likely, I would expect it's probably similar used to a GPU. And programming, of course, you use their high-level frameworks of AI, Kit, whatever, something, and all the, unless you want to reverse engineer this, all the nitty-gritty details are hidden in their nice library frameworks, which obviously is how you write commercial software, not to reverse engineer their assembly coprocessor. It actually could theoretically be implemented in terms of ARM coprocessor. I actually don't know. We will see. Probably someday we will know. But the ARM processors have a coprocessor interface, and usually the coprocessors already, there are some debug and floating point coprocessor stuff. So of theoretically 16 coprocessors. So, but I don't know if Apple used the standard ARM coprocessor interface. I would think that maybe it's more like a regular PCI GPU device, but kind of course not literally, but kind of anyway. Anyway, that's it for this video. Crazy level stuff here. I hope you learned something. Last but not least, Peter writes, now you can use Metal, but using GPU for some fancy, can my email notification, thankfully this wasn't live on the channel. Using GPU for some fancy processing magic would be nice. So yeah, it looks like it's locked down. Well, you can use the GPU to any fancy processing magic, right? You just program it with Metal or an Vulkan API wrapper. Certainly not GPL, certainly not OpenGL, because it is vastly outdated and in general outdated, and even more so outdated on Apple devices. So of course you use Metal or normally you would use Vulkan, just that Apple obviously boycotts Vulkan, so you use either their stuff or some like Molken or whatever, the open source OpenCL Metal wrapper, like what is it pronounced, like Metal, yeah, Molten, Vulkan. Wait a second, this is or is this not on? No, I think Molten. MoltenGL on top of here. So that is some solution for that. But so yeah, I mean, you can fully use it. How it's similar, obviously. NVIDIA also doesn't disclose anything, which obviously we recurrently shout out this. Todd asks, are you working with Hector Martin doing the sport? No, I'm not doing the sport. I just wrote you some software. I know him a little bit. I met him once or twice. He probably doesn't remember me, but I'm not. I was actually thinking with growing this YouTube channel, I was actually thinking like he to port this, but I actually decided not to because for the simple reason that I didn't want to spend like a year of my lifetime reversing, and because right now I'm flexible, as you see on these videos, every day or others every second day, some different topic here. And if I would have dedicated bringing Linux to the Apple M1 stuff, then this would have been at least a year, if not with the GPU and other stuff, a decade of work. And I didn't want to commit of 1 year, because actually the point of this YouTube channel, if you have not realized, is actually for me to do other stuff, because for 20 years I've done this T2 Linux that a few people are using, this just raw amazing open source Linux for stuff like the SJ Octane and PS3, but also like streaming from my own source Linux here. But the YouTube channel is actually not also insane. The old driver before I've completely written it in more amazing for ExactScan for mostly Mac is actually insane. Backends, the AVision backend for AVision and other OEM scanners, I think two. In the meantime, a decade later, over 500. Fujitsu, Canon, Panasonic, Visioneer, Xerox, Brother, and a couple of more. So yeah, after 20 years of Linux distribution and scanner reverse engineering, could imagine. So for your entertainment and education, but also my own fun, this YouTube video of just doing different stuff and allow me to do much more diverse topics than just sitting each day and doing each day Linux or scanner drivers that after 20 years. Yeah, boring, obviously. And this is why I didn't want to commit for another year or 20 years of Apple M1 stuff. And this is why I've intentionally chosen not to work on that. Also, in general, I don't want to promote or support Apple's proprietary stuff. I purchased this developer transition kit only under protest, as you have seen here on this video. And in general, I didn't, even with this Mac software, I didn't buy a personal Mac in 6 years. And the new one is only the developer transition kit, which I'm not allowed to talk too much about, except show you some probably it right, what could possibly go wrong, like here. Anyway, so yeah. But what will come soon is more microkernel, more just-in-time code generation, and in general, more fun and epic thread-ripping Ryzen. So yeah, that's it for today. I hope you learned something. And don't forget to share, like, and subscribe for all the fun, educational, diverse videos to come.